In this video, we're going to learn how to use ice tables to determine an equilibrium constant, or we can use them to help us determine the equilibrium concentrations of either reactants or products. So to ease into ice tables, what you got to know is that ice stands for initial change in equilibrium. So for all of these, we're going to be talking about the initial concentrations of reactants and products, how the concentrations are changing, and then the equilibrium concentrations of reactants and products. So we'll write that over here. So by chemical species, I mean reactants and products. So, for example, Homer Simpson loves making bacon sandwiches on Saturday afternoons. 2 pieces of bread and 3 pieces of bacon make 1 sandwich. Now, if we have 12 pieces of bread and 8 pieces of bacon in the fridge, how many whole sandwiches can be made and how much bacon and bread is left over? Okay, so here we're just using this example to help ease us into what ice tables can help us to figure out. Okay, and also how to use ice tables. So initial, that's going to be what you're starting off with. So we're told in the question that there's 12 pieces of bread and 8 pieces of bacon in the fridge. So that's why we start off with 12 and 8 in the bread and bacon columns. And since we haven't made any sandwiches just yet, that's why sandwiches or our products are 0 right now. So it's going to be the same for reactions, where if the amount of products isn't mentioned, you're going to assume that you have a 0 concentration of products, and you're assuming that you are starting out with only reactants. So in this case, bread and bacon. So we need to figure out how many sandwiches in total we can make. Now, we're told in the equilibrium row that we made 2 sandwiches. So we can assume that for the change row for the sandwich column, that this is plus 2, because how you get to 0, from 0 to 2 is you add 2. Okay? Now, since we made 2 sandwiches, we need to figure out, okay, how many slices of bread were used up. So we're told that 2 slices of bread make 1 sandwich. So if we made 2 sandwiches, that would use up 4 slices of bread. And if we made 2 sandwiches, since there's 3 pieces of bacon to make 1 sandwich, that would mean we used up 6 pieces of bacon to make 2 sandwiches. So for our equilibrium concentrations, what we're doing is we're taking 12 and we're subtracting 4. So that's going to give us 8. And then for bacon, we're taking 8 and we're subtracting 6. So that's going to leave us with 2 at the very end. Okay, so that's how you fill out an ice table when you have lots of information given to you. So again, with the initial, what that means is you write in what you're starting out for those reactions.
Steve, did they leave then? They'll just come back later or what?
Yeah.
Okay.
Meanwhile, the change row is talking about how much are your quantities changing by. And equilibrium just means what is the remaining amounts of each substances when the system reaches equilibrium. So as a reminder, equilibrium does not mean you have an equal amount of each substance on your reactants and products side. Okay, so if you wanted to split up all of these columns into reactants and products, remember that your bread and bacon, those are your reactants, whereas the sandwich is the product. Okay, so the blurb underneath here just goes over what I've talked about here, okay, but it does apply it a little bit more to how actual ice tables will look. So for the initial, that's where we're going to be talking about the concentration of reactants and products before any reaction takes place. So unless the problem specifies that products are present before the reaction happens, you can assume that the concentration for your products is going to be 0 for your initial row, only for your products. In the change row, that's going to show you how the concentration of your reactants and products change as the reaction proceeds from initial to equilibrium. Now typically we use an X to denote the change, and the number in front of the X always matches the coefficient of the molecule above. So it's going to be very important to write out a balanced chemical equation. So X is going to be negative for when you're decreasing concentrations, and it's going to be positive for when you're increasing concentrations. For the equilibrium row, that's going to talk about the concentrations of reactants and products after equilibrium has been established. X can be solved for using this formula, which is just initial plus change is equal to equilibrium. Okay, so that's going to be helpful later on. Now, the 4 steps for solving ice table problems is, first step, you need to write out a balanced chemical equation. Second step, you need to make an ice table. So you need to fill in the ice table with the concentrations that are given to you in the question, although you might need to calculate them first. So most of the time, if you do need to figure out the concentrations of for your ice table, then you can use this formula. Concentration is equal to moles divided by volume. So remember, concentration is always in the units of moles per liter. N for moles, that's in the units moles. And volume is going to be in the units of liters. Now step 3, you're going to solve for the equilibrium concentrations for each substance. And step 4, you need to write out the equilibrium law expression and then calculate the equilibrium constant using the equilibrium concentrations. All right, so for example number 1, the following occurs in a 1 liter sealed flask at a constant temperature. So we're given 0.2 moles of hydrogen and 0.1 moles of nitrogen. They were initially placed in the flask. Once equilibrium is reached, there are 0.080 moles of ammonia present. We're asked to calculate the equilibrium constant. All right, so let's start out with our balanced chemical equation. So I'm going to use purple to talk about that first step there. Okay, so we're told initially we have hydrogen and nitrogen here. Okay, and then it produces ammonia. And now we need to make sure that this is a balanced chemical equation here. So I'm going to go 2 over here. So why I'm doing that is because I have 2 nitrogens on the reactant side. If I put a 2 coefficient here, then I have 2 on the product side. But that 2 doesn't just affect nitrogen, it also affects hydrogen. So on the product side, I now have 6 hydrogens. So I want to make sure I have 6 hydrogens on the reactant side. So I'm going to put a 3 coefficient in front of hydrogen here. All right, so now that we have our balanced chemical equation, now I'm going to write out my ice table. So I'm putting these lines to separate out the reactants here, and then I'm also going to put a line underneath the equilibrium arrow so I can separate my reactants and products. I am going to make this line a bit thicker just so it's easier on my eyes to tell the difference between reactants and products. Now remember, all of the substances in here, they're all going to have to be measured in moles per liter. Okay, but the problem is that they've given us our initial amounts in moles. So in order to figure out moles per liter, we need to take the volume of the flask and the moles and divide them together. So what I'm doing here is for hydrogen, I'd take the 0.2 moles divided by 1 liter. That's still going to give me 0.2 moles per liter. Okay, so I'll show my work inside the box here actually. And I'm going to do the same for nitrogen. So 0.10 moles divided by 1 liter. That's going to give me 0.10 mole per liter. And the concentration of the product wasn't told to us, so we can assume that it is 0. Because at the initial stage, we're imagining that we are only looking at the point in time in which the scientists just put hydrogen and nitrogen into the flask, but they haven't yet reacted to produce any ammonia just yet. Okay, so now with the change phase, this is where the X's are going to come in to denote change. So this part right here. Okay, and remember that the number in front of the X is going to match the coefficient of the molecule above. Okay, so since we only have reactants and they are reacting together to produce products, that means we're using up reactants and we're gaining products. So that means I'm going to go minus 3x. The 3 is coming from the coefficient for hydrogen because this entire column, this entire first column right here is talking about what's happening to hydrogen. Okay, now for the next column, that's talking about what's happening to the concentration of nitrogen. So we're using up nitrogen in order to produce ammonia here. So we're going to go minus x because there's a 1 coefficient in front of the nitrogen. And then for ammonia, I'm going to go plus 2x. The 2 is coming from the coefficient of the balanced chemical equation. All right. So what else do we have here? We're told once equilibrium is reached. So that tells you that this information goes in the equilibrium row. There was 0.080 moles of ammonia present. So I'm going to fill that in my ice table. Okay, and I'm also going to calculate it in terms of concentration. So there's my moles divided by 1, 0.080 mole per liter. All right, but the problem with filling in the rest of this table, so the E or equilibrium values for hydrogen and nitrogen, is we don't really know what X is. So we need to figure that out so that we can figure out these values here so we can calculate the equilibrium constant. So I'm going to write out what I said just below here. So we need to figure out what X is, and how we're going to do that is we're going to use the chemical species that we have the most information for. So in this case, it's going to be ammonia. We have, or we were able to fill out the most in the ammonia column, so that's why we're using this column to figure out what X is. It's just because we have the most information for it. Okay, so we need to figure out what X is. This is where we're going to use the initial plus change is equal to equilibrium. Okay, so this is a formula that's going to be very useful in ice tables. So I'm going to take the values that we have in the ammonia column here. So initially we had 0, the change is going to be 2x, and then the equilibrium value is going to be 0.08. So then I'm going to isolate for X. So I'll clean this up a little bit. So I'm going to divide each side by 2. So then our X value, if I figure that out, that's going to be 0.04. And that's going to be moles per liter, because remember, everything in this table is represented in moles per liter. All right, so now that I have what X is, now I can figure out the equilibrium values for hydrogen and nitrogen. So I'm going to have to squeeze that in here. Okay, so again, we're following this I plus C is equal to E. So initially for hydrogen, we had 0.2 moles per liter. Okay, and then you can go plus negative 3x for the change, and then equilibrium value we don't know yet. Okay, so cleaning this up a little bit, we're going 0.2 minus 3x. And what I'm going to do is I'm going to substitute in our value for x that we just figured out. Okay, so that was that 0.04. So putting this into my calculator, 0.2 minus 3 times 0.04, that's going to give me 0.08. And remember, this is in moles per liter. Okay, so this is the concentration of hydrogen once the system has reached equilibrium. So we're going to do the same thing for nitrogen. So again, we're using I plus C is equal to E. So we're figuring out the equilibrium concentration of nitrogen here because we are in the equilibrium row. So positive times a negative is a negative. I am going to substitute our value in that we got for x. That's that 0.4. Okay, so if I go 0.1 minus 0.04, we're going to get 0.06. And again, remember this is in moles per liter, so I'm going to write that out. Okay, so that is the equilibrium row filled out. So now we can calculate the equilibrium constant. The reason why I had to fill out this last row here before I could calculate the equilibrium constant is because the equilibrium constant only uses values from the equilibrium row. Because otherwise, if you don't take from the equilibrium row, then you're not figuring out the equilibrium constant. So find the equilibrium constant using only values from the equilibrium row in the ICE table. Okay, so I'm going to do a quick equilibrium law expression. So remember, it's always products over reactants. So my products, that's going to be ammonia, and it's raised to the power of the coefficient, so that's going to be squared because of the 2 coefficient in front of ammonia, divided by hydrogen raised to the power of 3 because of the coefficient in front of hydrogen, times by nitrogen. Okay, so just as a heads up, for your balanced chemical equation, it's very important to include states there, but for your equilibrium constant, because we're not writing out a reaction equation, you don't need to include states in your equilibrium law expression. All right, so now that we have that done here, if it really bugs you to not have a number after the concentration of nitrogen, you could put a 1 there if you really wanted to, but if you're only writing a 1, you don't necessarily have to write it out, okay? Because we assume that if you're writing nitrogen there, it's to the power of 1 if you don't write a number for your exponent. All right, so let's plug in our values. So with ammonia, that was 0.080 squared divided by hydrogen, so 0.080 cubed times by nitrogen all right. So when I'm putting this in my calculator, I'm going to make sure to put my denominator in brackets just so my calculator doesn't get confused. So I'm going to go 0.08 squared divided by bracket 0.08 cubed. I'm going to press the right arrow to get out of the exponent times by 0.06. Close the bracket, hit enter, so I'm going to get 208.3 repeating. So I'm going to put a line over top of the 3's to mean that it goes on forever and it repeats. All right, now let's look at our question here to determine how many sigdigs we need to have this answer in. Okay, so it looks like the 1 and the 0.20 and the 0.10, those are all 2 sigdigs. Okay, same with the 0.080, that's just 2 sigdigs, so my answer needs to be put into 2 sigdigs. So then counting from the far left-hand side, 1, 2. So there's my cutoff line. So if your cutoff line is in front of the decimal there, then that tells you that you need to report your answer in scientific notation. Okay, so what we're going to do for scientific notation, you have to make sure there's only 1 digit to the left of the decimal that is not 0. Okay, so that means I got to move the decimal over 2 spots to the left. So I get 2 point. Now, in front of my cutoff line, there's a 0, but afterwards it's an 8. So the 8 is going to round up that 0 to a 1. And then I got to go times by 10 to the power of. So the exponent represents how many spots over you move the decimal. So I move the decimal over 2 spots to the left. Okay, and whether the exponent is positive or negative depends on if your original number was bigger or smaller than 1. Okay, so when your number is bigger than 1, then your exponent is going to be positive. When your original number is between 1 and 0, then your exponent is going to be negative. So in this case, I'm going to leave my exponent as positive. All right. Also, remember that equilibrium constants, they do not have any units, so I leave it like this. So that is my final answer. Okay, so this equilibrium constant is quite large. It's a whole lot bigger than 1, so that means this equilibrium constant tells us that our products are being favored at equilibrium. All right, in the next example, we're given the following equation. An amount of ammonia is placed in a 1-liter vessel and allowed to reach equilibrium. At equilibrium, there was 0.655 moles per liter of hydrogen, 1.230 moles of ammonia. What concentration of ammonia was originally present? Okay, so just a heads up, there is an error with this answer, so ignore that. So we're going to start all over writing our balanced chemical equation first. It's already given to us, so I'm just going to rewrite it up here. So again, I'm just making this line thicker to help me separate my reactants from my products. There we go. Okay, so let's look at what we're given. So it says at equilibrium. Okay, so that means whatever comes after this, that's going to be information that tells us what goes in the equilibrium row. Okay, so what do we got here? We've got 0.655 of hydrogen. So that's moles per liter, so I don't need to do any initial calculations because my amount of hydrogen is already in or given to me in concentration, so that's good. So we're also given 1.230 moles per liter of ammonia, and we're not getting any information about nitrogen. Okay, so let's just work backwards here and talk about our initial amounts. Now the question says that if we look at this first sentence here, it says an amount of ammonia is placed in a 1 liter vessel. Okay, so it means that initially we only have ammonia because the scientists took a vessel and put in ammonia. Okay, and the initial row looks at ammonia before it starts decomposing into hydrogen and nitrogen. So we've got only ammonia here, but we don't know how much. And for the initial amounts of hydrogen and nitrogen, we're going to put 0 moles per liter. And that's because the initial row looks at when you only have ammonia and it's before it breaks down or decomposes into the elements that make it up. Now for the change row, because we start off with only ammonia and no hydrogen and nitrogen, we can assume that this reaction, the forward reaction, occurs as written. So that means we're going to go minus 2x, so we're using up ammonia to produce hydrogen and nitrogen gas. So plus 3x plus x. Okay, I just want to add in a little note here in the initial row. I've said this before, but I just want to write it down. If the question doesn't mention the concentration of the products, you assume it's 0. Okay, so our question is asking us what the concentration of ammonia was originally. So it's asking for this initial amount of ammonia that we don't know. So in order to figure that out, we need to figure out what x is. In order to figure out what x is, we need to use the information from the column that we have most filled out. So in this case, this is going to be the hydrogen column. Okay, and we're going to use that I plus C is equal to E formula in order to figure this out. So I'm just going to write out what I just said. So calculate X using the concentrations of hydrogen in this ice table because this is what we have the most information for. So I plus C is equal to E. We're using this formula. So looking at hydrogen, I is 0, C is positive 3x, E is 0.655. So I'm just going to clean this up a little bit. We're going to isolate for x by dividing by 3. So that's going to give us 0.2183 repeating. And remember, this is in moles per liter. All right, so now that we have our value of X, now we can use that in the ammonia column to figure out what the initial concentration of ammonia was. And again, we're using that I plus C is equal to E formula. So initial, we have no clue what the initial concentration of ammonia is. You could write it as what I've written it here, or you could leave it as I. Either way works. So we're going to go minus 2x from here is equal to 1.230. So what I'm going to do is I'm going to add the 2x over. And since we know what x is, I'm going to substitute that value in. If you really wanted to substitute that value in on the first step, you could have. Okay, so x was at 0.2183 repeating. Remember, I'm going to be using the entire raw number that I calculated previously. That's what the ... means. It means I'm using the entire unrounded number here. So when I put this into my calculator, what I'm going to be writing is 1.23 plus 2 times second function, and then the negative sign will give me the answer. Okay, close the brackets, hit enter, and there is our concentration of ammonia initially. So that's going to be 1.666. It repeats forever. Okay, the only reason why the last digit is a 7 is because they're just rounding the very last digit, just because it can't show the entire number here. All right, so now that we're using our final answer, or that we've got our final answer now, we need to figure out how many sig digs it needs to be put into. Okay, so it's very tempting to be like, oh, there's only one sig dig in this number, so our answer should just be 1 sig dig. Keep in mind, you only use the numbers for sig dig that you actually used in your calculation. Since we didn't use this number 1 in our calculations, we do not use it to determine sig digs. So SD just stands for sig digs. Okay, so looking at our other numbers here, this is 3 sig digs, this is 4 sig digs, so you always got to go with the lower amount of sig digs, so that means our final answer needs to be put in 3 significant digits. So I'm going to count from the left, 1, 2, 3, there's my cutoff line. So my concentration of ammonia is 1.67 moles per liter. All right, moving on to the third example here, we have hydrogen iodide equilibrium system represented below, so right here. We're also given the equilibrium constant, so it's 6.25. A certain amount of hydrogen iodide is placed in a 2-liter flask, and the system was allowed to reach equilibrium. Once equilibrium was established, the concentration of iodine is 0.5 moles per liter. What is the concentration of hydrogen iodide at equilibrium, and what is the initial concentration of hydrogen iodide? All right, so let's get our balanced chemical equation written out here. Okay, now we need to draw out our ice table. So I'm going to be making this line thicker just to help me separate my reactants from my products. All right. Now the question says that we have a certain amount of hydrogen iodide placed in a 2-liter flask, and then the system was allowed to reach equilibrium. So this unknown amount of hydrogen iodide, we can assume that that is an initial amount. However, since we don't know it, I'm just going to put a question mark here. Okay, and so the word I'm looking for to kind of tell me that I'm looking at the initial row is this word placed. All right, now since for the initial amounts, hydrogen and iodide was not talked about, that means that we can assume that there are 0 concentrations for both of these. So both of these are 0 moles per liter. All right, once equilibrium was established, the concentration of iodine is 0.5 moles per liter. So let's write that in. So we're asked what is the concentration of hydrogen iodide at equilibrium and what is the initial concentration of hydrogen iodide. Okay, so those are our two unknowns here. Now let's focus in on the change row here. Okay, so for filling the rest of what we can in, at least right now, since we're starting off with 0 moles per liter of both hydrogen and iodine, that means that we can assume, so since we're starting off with 0 moles per liter of hydrogen and iodine, but we do have a certain amount of hydrogen iodide, we can assume that initially we have only hydrogen iodine in, but then the backwards reaction occurs in order for the system to reach equilibrium. So what that's going to mean in the change row is we're going to go minus 2x. The 2 is coming from the coefficient on hydrogen iodide. And then, since it's the backwards reaction, we're using up hydrogen iodide to produce iodine and hydrogen. Okay, and for the x's for hydrogen and iodine, it's only going to be 1x because both of these just have a 1 coefficient in front of them. Okay, so at this point, we need to figure out what exactly is x, and the column that we can use to figure that out is going to be the iodine column because that's what we have the most information for. Okay, so use the concentrations for iodine to figure out x. So we can use I plus C is equal to E. Now some people may just be able to look at this and figure out exactly what x is because you're going from 0, you end up at 0.5. What could x be? Well, x is going to be 0.5. But to show your work for that, how you'd show it is you'd go like that, and then x is equal to 0.5. Okay, so now that we have x, now we can find the equilibrium value for hydrogen iodide. So we're going to do that by using the equilibrium law expression for the system. Okay, the reason why I'm going to use the equilibrium law expression is because we were given the equilibrium law constant, and at least right now we don't have enough information just in the hydrogen iodide column to figure out what the equilibrium value for its concentration is. So Kc is equal to, it'll be concentration of products divided by concentration of reactants here. So writing this out really quickly, hydrogen iodide, which has a coefficient of 2, so I'm going to square it, divided by our reactants, so hydrogen and iodine. Both of them have a coefficient of 1, so that's done. Now I'm going to plug in our equilibrium constant, 6.25. And then I'm going to plug in the values for each of the concentrations in the equilibrium law expression. Now you got to remember that the equilibrium law expression is only going to take values from the equilibrium row. So in this case, I'm going to first just finish filling out hydrogen, And it's going to be the same situation that happened for iodine here. So 0 plus x is equal to what? Well, we figured out x was 0.5. Therefore, this is going to also be 0.5 moles per liter, because again, our x is 0.5. So 0 plus 0.5, that's how I'm getting this. All right, so now I'll keep on going with this. Hydrogen iodide. And then both of these are 0.5. So 6.25 is equal to concentration of hydrogen iodide squared. Now 0.5 times 0.5, that's going to give us 0.25. And what I'm going to do to isolate the hydrogen iodide is I'm going to times both sides by 0.25. So then 6.25 times by 0.25 is equal to 1.5625. So I'm going to have to move this up a bit here. So that's going to be equal to our concentration of hydrogen iodide. Now, since this is squared, the opposite of squaring is square rooting. So that's what I got to do. And what I do to one side, I have to do to the other. So we're going to square root our answer. So that gives us 1.25 is equal to the equilibrium concentration of hydrogen iodide. Okay, so we can write that in right here, and this is moles per liter, which I'm going to add these units here. Okay, so it's a very important thing to remember that the E row, that only talks about the concentrations for each substance specifically at equilibrium. Okay, and the reason how we know that this is for the concentration of hydrogen iodide at equilibrium is all of the concentrations we used, the 0.5s for hydrogen and iodine, those are from our equilibrium row. Also, the equilibrium constant can only be used to figure out equilibrium row concentrations. Okay, so we got that figured out. Now we need to figure out what is the initial value of hydrogen iodide that was placed in the flask. So for that, since we have values for C and E, that means we can use the I plus C is equal to E equation. So we're looking for the initial. The change was negative 2x. And the equilibrium value was 1.25. So I'm going to add over. So what I'm going to do here is I'm going to plug in a value for that we got for x. If you really wanted to, you could add the 2x over and then plug it in. Doesn't matter which way you do it, it'll get you the same answer in the end. So our x value, we figured that was 0.5. So 2 times 0.5, that's going to give us 1. So I'm going to add this 1 over. So we get that, and our units are moles per liter, and that is done. So I'll put a blue box, a dark blue box around my answers here, and then I'll fill that in here as well. Okay, so what I'm gonna do just before I finish off this example here is I'm gonna capture what I've already said just about this equilibrium row and equilibrium law expressions here. I just want to write it down. So this row is where the equilibrium law or the equilibrium constant is applicable. It's not applicable in the change row or the initial row. Okay, and the values that we've got here, they came from the equilibrium row. All right. The last thing that I want to mention that I just didn't say it out loud, was I've put all of my answers, so these two answers, in the correct amount of sig digs. So if you look at the question, yes, there's 2 liters here, so that was 2 sig digs, but we never used this number in our calculation, so we didn't use this for significant digits. Meanwhile, the number that we did use, which was this 0.500, that had 3 significant digits. Same with our equilibrium constant, that had 3 significant digits, so that's why my final answers were both in 3 significant digits.